Okay, so we're returning to section 11.2, applications of the geometric series. So remember, a geometric series will converge if the geometric ratio r is within 1, or the absolute value of r is less than 1. So here, we're going to learn how to create or express a decimal that is a rational decimal, a repeating decimal, or an ending decimal as a ratio of two integers. So here we're going to do example B, and maybe we'll do example A in class. So first off, I just want to go back to my pre-algebra skills and expand 1.035, that repeated decimal, in expanded form. So 1.035 is going to equal 1.0353535 dot dot dot. And that's going to be 1 plus 0.035 plus 0.00035 plus 0.00035 plus dot dot dot, right? So we would just keep adding. So then I want to break this down and say I'm just going to keep the whatever whole number that I have and just keep repeating that down the line. So let me just create this bigger and do this in a little blue. We just don't want to forget to add that in our final calculation, but I'm going to continue writing this one in term, so I can find it in terms of an A plus an AR plus an AR squared, or AR squared plus dot dot dot. So this would be my geometric series. And we can verify if our R is, if the absolute value of R is less than 1, then we know that our sum is going to converge to A over 1 minus R. So now I'm going to start rewriting the second, these guys in here, in terms of an A times an R. So we want to identify here that we see that A is 0.035. So I'm going to say that this is, I'm going to keep my 1 plus, and this is going to be 0.035 plus 0.035 times what? And we notice that the 35 portion is what I'm adding. So how many decimals does that take up? We want to actually say that that's times 0.01, right? And if I were to multiply by 0.01, I would be moving the decimal back over, and I would have my 3 zeros as I needed. Good. And so the next one would be plus 0.035, and this should be 0.01 squared, right? Because if I were to go back 1, 2, that's 0.0, oh, that's 0.01. And then if I do another one, taking left, if I multiply those two together, I would get 1, 2, 3, 4, 5, and that's how many zeros I have there. Good. So we see that, and plus dot dot dot. So now I can tell that my A here is going to be 0.035, and my R here is going to be 0.01. I see that the absolute value of R is less than 1, so we know that the sum is going to equal A over 1 minus R, and that's going to be, and if we rewrite 0.035 as a fraction, that would be 35, and this is 35 thousandths, so it would be over 1,000. And R here would be 1 over 100, or 1/100th. So if I rewrite those as my fractions, I do see that I have 35 over 1,000 divided by 1 minus 1 over 100. And I tend to like to multiply on top and bottom by the lowest common denominator. And the lowest common denominator I see is 1,000. And if I do that, I end up with 35 in the numerator. And if I distribute that 1,000, I do get 1,000 in the denominator for the first one, and then minus 1,000 divided by 100 is going to give me 10. And so I would end up with 35 over 990. And if I simplify that, what do I get? What does 990 going into 5 equal? I get 1, and then 4, and then here I would get 9, and I'm going to get 45, which is 40, 198. Good. Then don't forget that my 1 plus my 0.035, or plus this is going to be my final sum, right? Because we want to not forget that we're still adding 1, and we should end up with an improper fraction since we do have 1.0353535. So if I'm going to add my plus 7 over 198, this is going to be 198 plus 7 over 198. And so I end up with 2005, right, divided by 198. Good. And we should be able to verify that on a calculator. This one. For what values of x does x to the 2k equal 4? So if I rewrite this, remember I do see my k equal to 0. So I do want my n equal to 0 of ar to the n to equal a over 1 minus r, and not the r to the n minus 1. So if I rewrite x to the 2k with my k as my index, I do know from exponent laws that x squared to the k is going to give me my r to the k that I need. And also I can see that x to the 2k is going to equal 1 times x to the 2k, which is 1 times x squared to the k. And that up here is going to equal my a times r. Good. So we do have that a is equal to 1 and r is equal to x squared. So if my sum, as long as x squared is less than 1, my sum is going to equal a over 1 minus r, and that's going to give me 1 over 1 minus x squared. Good. So if my sum equal to a over 1 minus r were to equal 4, like it does up here, we want to be able to solve for x. So we can say, when does 4 equal 1 over 1 minus x squared? And now I can solve for x. So if I multiply on both sides, I end up with 4 times 1 minus x squared equal to 1. That's 4 minus 4x squared equal to 1. If I subtract 1 from both sides and add 4x squared to both sides, I end up with 3 is equal to 4x squared. 3/4 is equal to x squared. And so my solution would be plus or minus 3/4 would equal to x, or if you want to write that, square root 3 over 2, plus or minus. Good. So that's just a way of playing around with geometric series manipulations. This one's kind of fun. Let's take a look at this. It says a ball is dropped from a height of 10 feet and bounces. Each bounce is 3/4 of the height of the bounce before. Find the total distance traveled by the ball before it comes to a stop. So let's think about this. we know that the total distance traveled is going to be the bounce down, or the distance down, plus the distance up, right? And so the distance down here is going to be the first initial 10, right? And then it's going to it's going to go back up to 3/4 and it will bounce back down again. So we would have 3/4 of 10 to go back down again. And then when it goes back up, it's going to go 3/4 of that distance. And so, oh, sorry about that. Just kind of moved it a little bit. So when it goes back up again, it's going to go 3/4 of the 10 and 3/4. And when you multiply, if you do 3/4 of something, you're multiplying by 3/4. So we would end up with 3/4 squared, and 10 times, again, going back down again, it only goes back up 3/4 of the distance, and so it will travel again back up, dot, dot, dot. But what is distance up? Well, remember, it was dropped from 10 feet, but it never went up 10 feet, right? So the distance up is not going to have the 10 portion. So we would just have 10 and 3/4. That's the first distance that it goes up. And then it's going to go down that 10 and 3/4 distance, but it's only going to go back up 3/4 of that. So again, we still have 10 and 3/4 squared plus 10. And again, by the very same reasoning, when it goes back up again, it's only going to go 3/4 of the previous distance. And when it went back down, it's back down and it went that distance back up. So we have a plus dot, dot, dot. So looking at this, if we see inside and take the first one as the a plus a times r plus a times r squared plus a times r cubed plus dot, 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 we see that it is a geometric series. And we can say that the total distance down plus the total distance up, noting that the second one doesn't have the a, and that a is equal to 10, we can say that this is going to equal 2 times the sum of n equal to 0 to infinity of 10 times 10 to the 3/4 to the n, right? But then we want to, if it's twice that, well, what one piece are we missing? We'd have to subtract out that 10 feet, right? Because it is missing here. It's missing here. Good. So we see that this is a geometric series with a equal to 10 and r equal to 3/4. Since 3/4 is less than 1, we can say that the sum here is equal to a over 1 minus r. You can't use that if it diverges. It just diverges if r is bigger than 1, or the absolute value is. And so we just plug in those values. So we have 10 over 1 minus 3/4, and that's going to be 10 over 1 and 1/4. And then when we have, this is going to equal 40. But now my total distance then, don't forget, is going to be 2 times that sum, and then minus 10. So this is going to equal 2 times 40. And then we still have the minus 10. And we end up with 80 minus 10, or 70. And we want to make sure that we have the right units of measurement, and that is 70 feet. So that's kind of fun. And any type of percentage of, or less than a percentage of the whole, and you're summing them up, you can use this type of reasoning using geometric series. Another example might be a company plans to sell 20,000 cars in the first year and 80% with each subsequent year. How many cars does the company plan to sell over the lifetime of the car? So you can say 20,000 plus 80%, 20,000 for the second year, plus 20,000 times 0.8 squared, because it will be 80% of the previous year, and the previous year was just 80% of the previous year. So you can set up a geometric series, and since 80% is a proper fraction, r is less than 1, and you can find the total number of cars. So it's kind of a fun thing. The next video will be on telescoping series. Thanks for watching.